So today I'm going to be following up on what yesterday we talked about the temporal discretization, and that's kind of how the whole algorithms fits together. Today I'm going to be talking about a number of the key spatial discretizations, in particular in the dynamic core of MOM6. Alistair talked yesterday about the parameterizations. There are lots and lots of them. The dynamic core is a little bit more limited, and so it's worth spending a little bit of time going through. Now, I'll be talking about the Coriolis terms, which appear in the momentum equations, how we treat the continuity solver, the pressure gradient terms, and in particular, how we handle the pressure gradient terms with the nonlinear equation of state, and then finally, a couple of words about how we treat vertical viscosity and diffusion, which was something that Alistair touched on yesterday, but there's some specific aspects of what we're doing. The takeaway, one of the key points about MOM6 is that we extensively test MOM6 to ensure that all of the discretizations will work in any part of parameter space that we find ourselves getting into. These are climate models, and climate models have a way of finding every obscure part of parameter space at some point or another. And so we've aggressively tested these, including in the limit where we have vanishing layers. And the vanishing layers are important if you're an isopycnal coordinate model, because you can have water that is simply lighter in the water column than the target values, which is how these came about. But it's also important for things like wetting and drying due to the tides, or having the coastlines move, or having the ocean be squeezed out by ice sheets. And one of the kind of the key principles that I think we think about when devising the numerics and the spatial discretizations in MOM6 is Murphy's law, that whatever can go wrong will go wrong, or one of my favorites, the ocean modeler's corollary to Murphy's law, namely that ocean models are Murphy's law machines. So MOM6 is discretized on an Arakawa C grid. This is terminology that's specific to the atmospheric and oceanic communities. Other communities would simply describe this as a staggered grid, because there's no reason why you would ever choose any other staggering, but there are in fact A, B, C, D, and E grids. The C grid is particularly good for representing the convergence and divergence of flow for tracer transport and for representing gravity waves. But because the U and the V points, which are discretized in this plan view map here with arrows to the right and arrows to the up, are staggered relative to one another, we have to average, even in the linear limit, the U velocities. 4 adjacent U velocities have to be averaged to get them onto a V point, and conversely, 4 adjacent V velocities have to be averaged to get them onto the U point. By contrast, for the continuity equation, we use a simple second order staggered discretization that works remarkably well. One consequence of this averaging is that the representation of a geostrophic balance on a C grid is that the average of 4 adjacent velocity points balances the gradient of the pressure field, or in this case, the surface height. It also has consequences when it comes to the gravity wave dispersion relation, which looks pretty good, except when you get down to the grid scale, the gravity waves are essentially non-rotating. So you don't have geostrophic balance for the 2 delta X motions. They can simply radiate away. And that also shows up in terms of the Rossby wave dispersion relation, where there are some distortions at the grid scale. The longstanding takeaway in the oceanographic and atmospheric community is that if you are running in the limit where the Rossby deformation radius is not well resolved, then a C grid is problematic. And the reason is because you can't represent geostrophic balance at scales where geostrophy should apply pretty well. But as you get to the limit where the Rossby deformation radius is well resolved, a C grid is kind of the grid of choice for many purposes. It does a really good job of representing the gravity waves, and because when the deformation is well resolved, the scales at which geostrophy applies are also well resolved, and a C grid does pretty well. And so increasingly over time, we in the oceanographic community have shifted from a B-grid discretization, as was used in MOMS 1, 2, 3, 4, and 5, to a C-grid discretization, such as is used in MOM6, HICOM, ROMS, and NEMO. Now, there is one computational null mode on a C-grid, or actually a pair of them, namely that you can have streams of velocities in alternating directions of equal magnitude. And if you look at the averages in the linear shallow water equations, these null modes, because of the averaging that we have to do in the Coriolis term, they don't do anything in the Coriolis terms. Because they're non-divergent, they don't do anything in the continuity solver. And so if these modes are excited, there's nothing in the linear envisaged shallow water equations that makes them dissipate. They can just persist without any real physical meaning. In practice, the way that we handle that is by applying a lateral viscosity, either a Laplacian viscosity or bioharmonic viscosity, both of which are pretty effective at controlling and suppressing these computational null modes. But if you're running your model and you find these sort of streaming modes of the velocity in either direction, what it's telling you is that you probably need a stronger horizontal viscosity to control whatever nonlinear or forcing terms are exciting these null modes. The one nice thing about a C-grid is that there is no null mode in the pressure field or the temperature and salinity fields. If you have familiarity with an older B-grid model, they had this very well-known famous checkerboard instability, high, low, basically the red and the black squares of a checkerboard could be set to independent values. And the result of that is that you cannot have a forcing field, say a river flowing into the model, at a single point, or it will do a great job of exciting that checkerboard null mode on a B grid. With a C grid like MOM6, you don't have to worry about that. You can have forcing at a single point, no problem at all, and it will handle it, albeit as we noted, at the smallest scales, the two delta X modes are as though they're non-rotating. It will tend to slump out without being arrested by geostrophy. But that's kind of a forgiving mode of undesirable behavior for the model. So the nonlinear discretizations that we use tend to be straightforward for the momentum equations with one kind of critical piece. We invariably solve the momentum equations in vector invariant form. And so here I've written them in vector invariant form, where Q is the potential vorticity at the vertices of the tracer points. The right-hand side, or I've shifted it here to the left-hand side, the pressure gradient and the gradient of the kinetic energy are straightforwardly discretized. You're simply averaging the square of the velocities to get them onto the tracer points and then taking the gradients. That works out pretty well and is pretty widely used, although we do have some alternatives available in MOM6. One of the big kind of points of contention or where there are options is the discretization of that Coriolis term. And here I've written it as the potential vorticity times the total transports in the U and the V directions. Depending on how you discretize this form, you can retain certain nonlinear conservation properties. So for instance, in a classic 1975 paper, Sadourny explored two different discretizations, one of which conserves energy, which you can derive by taking the transport dotted into the two momentum equations, combining it with the Bernoulli function, that whole thing inside of the gradient with the pressure and the kinetic energy times the continuity equation, to basically get an equation that is written as the time rate of change of the total kinetic energy discretized at the tracer points, the green circles, plus the exact divergence of fluxes. And so this form of the equation conserves energy, but it doesn't conserve potential entropy, the square of the potential vorticity. By contrast, there's a different discretization, and I'm going to toggle back and forth and look at the equations in the top left. The only place where they're varying is in that Coriolis term and how we're averaging it. to get the potential vorticities combined with the four transports around a velocity point. And I'll go into this graphically in a second. But this alternate form doesn't conserve kinetic total energy exactly, but it does conserve potential entropy exactly. Now, the combination of conserving energy and potential entropy has this remarkable property in two-dimensional turbulence. The energy tends to cascade to large scales, the entropy to small scales, and as long as both of these quantities are exactly conserved, you are essentially enforcing this property of two-dimensional turbulence where the motions cascade up to the largest scales. This is why we have weather on a rotating planet, whereas if you stir up a non-rotating fluid, you just get a cascade of the energy down to the smallest scales where it's simply lost. You don't have large-scale coherent structures emerge. Obviously, we would like to emulate the properties of the atmosphere and the ocean, and so the conservation of these two properties is something that's worth considering. Now, there are a variety of different discretizations of these Coriolis terms that have been published in literature, and I'm illustrating them here schematically. The red arrow and the blue arrows are connecting adjacent u and v velocity points. There are four velocity points around, four northward velocity points around each eastward velocity points, and conversely for the other terms. Where the two terms, and here I'm just highlighting the stencil of the potential vorticities that are connecting these two adjacent velocities. Recall that there are four of these that contribute to this u velocity point. And the size of the stencil here is everything that will contribute to that u velocity point or that u velocity point contributes to. So Sadourny's 1975 energy conserving scheme is relatively straightforward. It has a connection taking the same potential vorticity in that corner point and connecting the two different, the u and the v points that are adjacent to each other. By contrast, his entropy conserving scheme, you have a different stencil for the influence of u on v from the influence of v on u. This is why it doesn't conserve energy. You don't have equal and opposite terms appearing in the two momentum equations. There have been other discretizations that people have devised over the years. A very well-known scheme of Arakawa and Lamb, 1981, uses an average of the four different potential vorticities around this kind of couplet of velocities, with weightings that the two on the diagonal are weighted twice as heavily as the other two. But he also has to add in some extra terms. I'm going to step away from the mic, sorry. Oh, maybe I can do it. Where this u transport in conjunction with these four potential vorticities is also contributing a term at the u point. It's the average of these, if the PVs are all the same, then it comes out to zero, but he adds in these other kind of strange unphysical terms in order to get the terms to balance. A later paper by Arakawa and Su, a different student working with or postdoc working with Arakawa, suggested instead that what you really care about is the entropy conservation in the non-divergent limit. In other words, the limit that is really exercised by quasi-geostrophy, in which case you can use a simpler stencil using the average of these three potential vorticities around this kind of couplet of points to give you the Coriolis term. And then in the divergent limit, now you're really looking at the gravity waves, which aren't really playing such an important role for the geostrophic turbulence. Now, the challenge here is that the formal conservation properties with all of these schemes depend on the use of a second-order centered discretization of the continuity solver. However, that second-order centered continuity discretization is not positive definite. So if I have a flow from a thick point, from a thin point to a thick point, and the thickness at this point in between is the average of the two, it is possible, depending on how large the difference between the thickness of the adjacent points is, for you to suck more water out of the cell than you actually have within the cell. gives you a negative thickness or a zero thickness, and this wreaks chaos throughout the discretizations, including that the conservation of kinetic energy, which is a positive definite quantity, it's the velocity squared times the thickness. If that thickness goes negative, then that's no longer a positive definite quantity. Conservation of kinetic energy doesn't buy you anything. Similarly, conservation of potential entropy. So instead, what MOM6 does is we use a directionally split piecewise parabolic method continuity solver. And we can do this either with a positive definite limiter or a monotonic limiter. And this is exactly what I described yesterday when we were talking about the tracer equation. So we're going back and using the same sort of approaches to determine the mass fluxes. And then once you know the mass fluxes, you use the ratio of the mass fluxes to determine how much tracer you move around. And either of these approaches, whether you use a positive definite or a monotonic limiter, are stable provided the sum of the outward transports in one direction out of the cell is less than 1. In other words, they work provided that you don't have such large velocities that you take out more mass from the cell, but that's something that's now based on the velocity magnitudes, not the thickness distributions. However, in order to try to retain consistency with all of the diagnostics and the analysis of the energy and the entropy conserving schemes, what MOM6 does for the unlimited edge values is we take the second order average of the two adjacent thicknesses. In other words, in the small flow limit, the weak flow limit, the small CFL limit, we go back to this scheme that was shown to conserve energy and entropy in the previous slides. The actual continuity transports that we use here, so the capital U's here are transports. There's a velocity times the thickness. The transports that we actually use are the actual transports used in the continuity solver, not the discretization, this simple discretization used in the formulation of these older analyses. Okay. So there is still one caveat in that with some discretizations of the Coriolis scheme, and here I'm picking on Arakawa and Su, which is a good scheme, you can have finite transports even if 4 of the thicknesses that are used to generate potential vorticity are all 0. So for instance, if all 4 of these points in the top right corner of this little schematic diagram are all 0, you can still have a non-zero transport here at this U point, and that U point transport is multiplied by 1/0 or an infinite PV to give you an infinite acceleration at this V point. Now that V point in this little hypothetical case has an infinite acceleration but 0 thickness. Maybe it's okay, maybe it's not. But the point is that your Coriolis scheme is not limited, and it could take on any values for kind of crazy distributions of the thicknesses. So there are a couple of things that we do to try to avoid that. One of them is the thicknesses that we use here in the denominator of the potential vorticity are the averages of the thicknesses at the tracer points before and after a step of the fluxes with the continuity solver. That helps. It makes it harder for you to have vanishing cells in the denominator, either before or after they tend to have had mass, but it doesn't help enough. And so the other thing that we do, and if you look into the Coriolis terms, you'll see some rather complicated code, but what it's doing is it's saying, okay, I have a separate way to estimate the Coriolis scheme at this V point and similarly at this U point, namely that I have either 2 or 6 potential vorticities that are kind of around that point, and I have 4 velocities, not transports, but velocities. I can take the absolute vorticity at these 6 points and the velocities, and that gives me 6 different estimates of what the Coriolis scheme acceleration should be. And so you take the largest of those and the smallest of those, and that gives you a range of plausible values. If you're outside of the range of plausible values, then you know that because of the weird thicknesses, that the energy and entropy conserving schemes are kind of doing the wrong thing. So instead, what we'll do is we'll take, depending on where you are, either the maximum or the minimum of that range of values, and it keeps things limited. And in those cases, invariably, you're dealing in the case where a lot of the thicknesses tend to be going to zero. And so your vertical viscosity or your horizontal viscosity is kind of able to come in and clean things up, but you have a finite acceleration. If it's an infinite acceleration, you're in real trouble. And with these limiters, all of the Coriolis discretizations in the MOM6 code base work with any combination of vanishing layers, including, for instance, even in this limit where in the bottom left with Arakawa and Lamb, where because it has such a big stencil, you're very likely to have, say, some corner point that's effectively over land or has vanished into the topography. And it's very likely that you will be having to deal with essentially infinite potential vorticities. And so basically we avoid that. The other thing that I think is worth noting here, and this is just in passing, and I may be stepping on Alistair's talk, everything in MOM6 is designed so that you have rotational symmetry. We do that by adding appropriate parentheses. So for instance, when we're discretizing this potential vorticity, it's the absolute vorticity but divided by an average of 4 adjacent thicknesses. If you just write it down as a quarter of the sum of these thicknesses, the order is completely arbitrary. You've left it up to the compiler. It can decide to add it up in any order. You don't know what result you're going to get. And so if you rotate things, you may or may not get an answer that's the same. On the other hand, if you write this average with a variety of seemingly plausible selections of parentheses, you can either get a form that has no rotational symmetry, if you kind of cluster it and you just add things in order as they're written, which is what most compilers will do. You can, the little boxes are the first average, the second average, and then finally you average the rest. You can see if you rotate that, this little pattern rotates around, you don't have symmetry. On the other hand, if you group things so that you're adding in the I direction first, well, that's fine for rotating by 180 degrees. But if you rotate by 90 degrees, then that equal sign becomes something going vertically. So what we do is we deliberately group things so that when you rotate them, you get rotational symmetry, as is the case where you add across the diagonals and then add the 2 diagonals. You'll see this throughout MOM6. And one of the things that'll strike you is you might say, there are a lot more parentheses here than you think are necessary. Most of those are there for things like rotational symmetry and to make sure that when your model fails in production mode and you run it in debug mode without all the optimization, it will fail in exactly the same way. So you can debug the model, figure out what's going on and fix it. Okay. So that's the Coriolis term. The pressure gradient force is one where the discretization might seem relatively straightforward. It is straightforward in the linear shallow water equations. However, we are dealing with a generalized vertical coordinate, and here I'm calling it A. And so using the hydrostatic equation, we can modify the hydrostatic pressure gradient along surfaces of constant Z into an arbitrary vertical coordinate. And so the first step is just kind of a general transformation of coordinates. So your gradient along surfaces of constant height becomes a gradient of along surfaces of an arbitrary coordinate plus a correction based on the slope of that of the geopotential height here. This is using the hydrostatic equation. So it's basically, it picks up an additional term due to the slope of Z along your surfaces of constant A. And you can combine these 2 equations into the gradient along arbitrary surfaces of a Montgomery potential minus the pressure times the gradient along surfaces of the inverse of density or specific volume. So the reason why I'm showing you this is that when you have these multiple different terms, they have to be discretized differently. And there's a non-cancellation of the truncation errors because they are discretized differently. They use different stencils and different terms. And that non-cancellation can be problematic if these 2 pressure gradient terms are of opposite sign, as is the case when your coordinate surfaces are outside of the range between surfaces of constant pressure and surfaces of constant density. In addition, when you have these two terms, if you take the curl of the momentum equation in order to get a vorticity equation, the first term, the curl of the gradient, drops out, but the second term, what you're left with is the gradient of pressure crossed along surfaces of constant A crossed with the gradient of specific volume along surfaces of constant A. Or if you kept things in the first term, well, it comes to the same thing. Okay, and so in order to avoid having these two separate terms, there are three different vertical coordinates that are a little bit special. If you have a pressure coordinate model, then you would write your gradient of your pressure gradient as the gradient along pressure surfaces of geopotential height. This is done in atmospheric models quite widely. Conversely, if you're in an isopycnal coordinate model, then you would write your pressure gradient as the gradient along surfaces of constant density of the Montgomery potential. If you are in a z-coordinate Boussinesque model, then the way that you deal with this is by simply saying, well, rho is approximately a mean density, make it a constant, and that does the same thing. But if you're working with a generalized vertical coordinate, you have a couple of problems. Now, one of the problems, and these problems arise to a significant degree from the nonlinearities of the equation of state. And so the top left are contours of constant potential density with a 0, 2,000 meter, 2,000 decibars, 4,000 decibars of pressure. And you can see that there are places where things may be stably stratified in one pressure or not in another. Similarly, you have a compressibility of water that is a function of temperature. And these both give rise to some problems. So if you take a density-like coordinate model and you just naively use in situ density, but your coordinate is a potential density, then that you still have this leftover term, which is the pressure gradient of in situ density along surfaces of constant potential density. Now, you can cancel that out by approximating things in the pressure gradient as though it's just the potential density. However, this gives a real problem in that it gives you pressure gradients of the wrong sign. And this is a very nice demonstration from a paper from 23 years ago now, where you have Antarctic bottom water on one side of the domain and North Atlantic deep water on the other side of the domain. These are two water masses that do appear next to each other in the ocean and can occur next to each other at the surface or at depth. But depending on which potential density you use for these two columns, you will have a gradient that either goes one way or the other. Whereas in reality, because of the nonlinearities of the equation of state, the black line here gives you gradients that actually reverse as you go down through the water column. At the surface, Antarctic bottom water, because it's fresh but cold and temperature doesn't have as much impact near surface pressures, Antarctic bottom water is lighter than North Atlantic deep water, whereas at depth, Antarctic bottom water is denser than North Atlantic deep water. And so you can't just approximate the density as though you can use potential density everywhere. You will get qualitatively the wrong circulation in your ocean. Your Antarctic bottom water cell, your North Atlantic deep water cell, completely wrong. One of them goes away. Sun et al. Suggested using the true in situ density to avoid this, but extracting a typical compressibility, which was a really good idea. You can make that term smaller. However, it turns out that when you extract a compressibility that is typical of the Weddell Sea, you get this unstable mode in the Mediterranean, which is weakly stratified but very salty. If you use Mediterranean-like properties, you get a computational mode over here in the Weddell Sea, and so you're kind of stuck between these two. However, if you extract compressibility appropriate of the Mediterranean on the left, you don't get this mode of instability, and similarly on the right. And so so one approach that we explored and quickly discarded as being simply too complicated was to have a spatially varying compressibility that we extracted. Instead, a really clever person realized that you can represent the pressure gradient force as an analytic integral around a control volume, and we can analytically integrate the hydrostatic equation in the vertical to give something that works remarkably well. So that whereas over here on the right, some of these instabilities that you can see as large excursions of the pressure gradient are essentially eliminated by using this analytic finite volume integral of the pressure, assuming a subgrid scale distribution, in this case of temperature between red and blue, but analytically integrating around this curve. For some equations of state, you can do this analytically. For others, you can use Boole's rule quadrature. In other words, subsample at 25 points, and the answers are the same to round off. And this works remarkably well. It's one of the things we've been quite happy about. And this is the analytic finite volume pressure gradient in MOM6. Now, if you're not using temperature and salinity as state variables, you can still go back to the traditional Montgomery potential form. That's available. The two give the same answers in that limit. But this is the one that's used in all realistic climate models, and one that we're pretty darn happy with. Now, there is one slight complication in that regardless of how you're calculating this pressure gradient, if you have layers that ride up over topography to basically they're vanished, but they're high on the one side, thick on the other, you have this kind of triangular wedge of fluid that is sticking up. It's much denser than it might otherwise be just based on the horizontal stratification. This can lead to a very large down gradient, downslope flow around topography. However, this flow is happening in masslessly thin layers. And so what we do in MOM6, following on something that goes, for me, way back to my days as a graduate student, is we use the balance that would really apply if you had a very thin sheet of fluid riding up over the topography. If it's thin enough, it's embedded in a viscous boundary layer, and it doesn't move. So we use an upwind biased estimate of the thickness in the vertical viscosity to arrest this downslope flow. This allows the flow to flood onto the fluid. It allows it to drain away, but once it gets thin enough, the viscous arrest occurs. This is essentially the same balance why if you paint a vertical wall, the paint just doesn't fall off. It's viscously arrested in a thin enough layers. And this does emulate the correct physical balance, and it's something that works quite well. However, we're now making different choices about the effective thickness at the velocity points than the ones we made in the continuity solver. They're broadly consistent, but this is one area where I think that there is room for improvement by treating the viscosities in similar ways. Now, the other part about this, and this is actually kind of a critical part of this, is in order for a vertical viscosity to work in the limits of vanishing layers, you have to write it in such a way that it will actually work in the limits of vanishing layers. If you read any textbook on numerical methods, almost anyone, for instance, like numerical recipes or something else, they will tell you that the right way to write a tridiagonal solver is to use something known as Thomas's algorithm. And so you treat this as a matrix problem. In this case, this is vertical diffusion of a tracer, but the same applies for velocity. You identify the diagonals, and then you go down through your matrix and you do Gaussian elimination. You subtract off various terms. The problem is with the traditional Thomas algorithm, this second step where you're kind of estimating the pivot, you have this subtraction in the denominator. And the problem is if B and A of k minus a half and q minus 1 are almost the same magnitude, as can happen for very thin layers with strong viscous coupling, you can get 0 in the denominator. That's a problem. However, you can rearrange all of the terms that I've defined up on the top of my tridiagonal solver, such that the calculation of the pivot, instead of kind of substituting to get everything into this B sub k, just leave it in the original form that you got from your diffusion equation. And now I can use the fact that these two terms that are potentially large and of opposite sign are proportional to the same value of A, the coupling coefficient with the layer above. And this 1 minus q that I get is something that I can calculate separately. The takeaway here is that I am able to calculate this entire tridiagonal system, the solution, without ever subtracting anything from anything else. I use division, I use addition, and I use the original mathematical expressions. And so this form on the right is something that is incredibly robust. There was an instance, this is about 12, 15 years ago, where GFDL had a computer that had a bad chip. And the nature of the badness of this chip is it would sometimes give you a random number in the least significant digit, which you think, okay, well, you know, of the 16 decimal places, the first 15 were fine, not a big deal. The MOM4 tridiagonal solver at the time was written as it was on the left. We took that tridiagonal solver and used it as a way to detect which chip was bad because it was so very sensitive to random fluctuations at that last bit. It was failing routinely. The MOM6 algorithm on the right would never have detected that because in this case, we're not taking any differences. The answers always have the full 16 decimal digits of precision without having to worry about some of the problems that can arise with round off. This is just one kind of very specific example, but a very good one. In this case, this is something as I was starting to write this up, I realized that Paul Schopf had realized exactly the same thing several years before and stuck this in the appendix of a paper where it mostly got ignored, but it's exactly the right analysis. So if you want to look at the Schopf and Longy analysis in his monthly weather review paper, it goes through exactly this problem, beautifully crystal clear. But this is just one example of the ways that we, in MOM6, go back and we look very carefully at the discretizations to try to figure out, are there better ways we can work, taking into account that we're dealing with discrete math, not continuous math, to try to get algorithms that give the right physical answers in all part of parameter space. So I'm just going to close here with a few thoughts about some areas of potential improvement in the MOM6 dynamic core discretization. Hopefully as a way of kind of soliciting people to think about ways that they might contribute. And also to kind of emphasize that although we're generally pretty happy with everything in MOM6, we think it's robust, we think it's well tested, there are still areas of opportunity. Please do contribute. So the first one, I think that there's a lot still to be done with the creative use of this generalized vertical coordinate capability. We know that we can emulate a variety of different coordinate systems. We know that the choice of effective vertical coordinate systems has a significant impact on the large scale circulations. So ideally, we could come up with formulations, for instance, that are as adiabatic as we are able to achieve with a kind of a layered isopycnal coordinate, but based on interface values so that you can gracefully transition to pressure-like coordinates near the surface where the stratification is weak and an isopycnal coordinate is a terrible idea, while simultaneously being able to represent oddities like the high latitude haloclines, where because of the dominance of salinity in the equation of state at cold temperatures, you have regions where the salinity dominates, and so the typical dominance of temperature in mid latitudes is flipped around. And so using any kind of a potential density formulation, it just doesn't work. I think there's a lot of benefit potentially from trying to go through and systematically use consistent estimates of the thicknesses at the velocity points. And I highlighted here that we're using thicknesses at the velocity points in the continuity equation. We're using those equivalent thicknesses for open boundary conditions and for the barotropic solver. But similarly, we're using these, but we're using different estimates of the thicknesses for the vertical viscosity. And this is one of the complications when Steve was talking about how we took the native grid balances and trying to recast them into a fixed z coordinate mode, that was one of the things that was tricky. A lot of it had to do with the fact that we're using different estimates of the thickness at different points in the algorithm. I think that's something that can be unified. Similarly, with the continuity solver, we're using a piecewise parabolic method with the second order edge values. I think we could actually do a bit better if we change to a quartic approach, because that allows you to use those same edge values that are consistent with the neighbors, but not have to restrict them so much to maintain positive definiteness. And so I think there's some possibilities there, either with or without directional splitting. If you did it without directional splitting, there are some simplifications that accrue. You could do the constructions once, save them, and then reuse them throughout the algorithm. I think what I've showed you today, there are 4 different discretizations of the Coriolis terms. There's actually a 5th one, which is kind of a weighted average, a limited average between these. I think this is an open area of exploration. We know, for instance, in the Neverworld 2 simulations that were used by one of the climate process teams, that the choice of the Coriolis discretizations matters, especially as you get into the limit where you're starting to do a reasonable job of resolving the geostrophic turbulence. And so the choices that might have been guided by coarse resolution climate modeling may not be the best ones going forward. And we could do this one of 2 ways, either by taking the existing Coriolis discretizations and combining them, or perhaps by treating the Coriolis terms separately from the advection of momentum terms, as is done in HICOM or ROMS, and then trying higher order schemes. And then finally, always at the bottom of our wish list is the idea of adding a non-hydrostatic or semi-hydrostatic capability to MOM6. It's a good idea, but it never seems to be so pressing that we need to intervene to take it on. So that's just kind of a quick tour of some of the key numerical decisions that went into the MOM6 dynamical core. I hope this has given you an appreciation of the importance of thinking about all of these different considerations of nonlinear conservation properties, energy, entropy, but also the importance of choosing numerics that will work appropriately, even in weird limits like vanishing layers or weird combinations of vanishing layers. I think we're doing really well with the make it work in weird limits, but I think there's still room for improvement in terms of discretizations that might work better, especially as we push increasingly to the limits of very high horizontal resolutions. Thank you very much. Yes. You can turn it off. If you turn it off, the Sadourny enstrophy scheme generally works. Sadourny energy. The other schemes may work for a while, but you might find yourself in a strange part of parameter space where it doesn't. They tend to work pretty well in idealized problems, but once you start getting outcropping of layers or incropping into the topography, that's exactly where you get into the limits where some of the thicknesses go to 0. And then you may be leaning very heavily on your vertical or horizontal viscosities to save the day. And then you found you needed them. And you don't need them very often. But the problem with a climate model is it has to work right everywhere for all parts of parameter space all the time. And having something that only fails 1 time in a billion, well, if you have 1 million grid points in the horizontal and 100 layers in the vertical, 1 time in a billion is 10 time steps. So you do find every weird case that could possibly happen over the course of a not terribly long run of a climate model.